Okay, so once again, you are mostly welcome. My name is Mtanda Samil. So, without wasting time, we are now in for our last item of our Jinja joint mock examinations, item 7. Okay, now what you must know is okay, so we are still proceeding with our Jjeb, and this is the last item. Of course, you all know that as per the standard paper, physics O level must have two papers, paper 1 and paper 2, where paper 1 in theory and strictly you're in for paper 1, which implies that paper 1 has only 7 items. Yeah, so for you when you're attempting, you know the numbers you're meant to do, but for us here, we tend to do all of them because why to leave out some? Alright, now, so without wasting time, let's go on to this item 7, but please, it is very, very enticing and has a learning point. Okay, so you must watch this video at the end and please consider sharing it to other people such that they also benefit. Alright. Yeah, I once again will remind you to subscribe to the channel, and of course please, I told you that sooner or later, okay, we shall be limiting this channel to strictly our subscribers. So if that time comes when you have not yet subscribed, it means that one, you will not be able to access the channel not until when you make some monthly payment. So why anyway to pay? Yet just a simple subscription gets you there. Okay, so don't miss out just because of a one simple click, which we are calling a subscription. Alright, good. So we are in for item 7. Let's get there. Okay, good. So let's go through it. Let's pen. Okay, they're saying it is a common problem in many villages in Uganda. The lights dim. Oh, that's very bad. The radio cuts out. So sad. And sometimes there is no power at all. Really, really bad. This happens a lot in places far away from the power plant, at the dam bridge in Jinja. Oh, anyway. Right. So the electricity then travels through very long wires to reach homes in different villages. Along the way, the power gets weaker, and the people in your villages have noticed that their appliances, like electric cookers, flat irons, fans, and lights, sometimes don't work properly. Some appliances are connected in a way that if one stops, the other do not work at all. Oh, anyway, that's again some bad news here. Alright, so let's proceed again. Our lesson. Okay, the people in your village are really puzzled and want to understand why their electricity supply is weak. How machines that make electricity, the changing current generator, in fact, not that, affect power they receive. How can how can they how they can figure out how much electricity or current is flowing through their own appliances at home, and why electricity is sometimes sent over longer distances using very high pressure or high voltage but very little flow. Very little flow. Okay, the bracket carry. Now here, what you see in quotes is what people think, and like in a layman's language, they can call it pressure. The power is coming at a very high pressure, but in actual sense, that in physics means voltage. Then little flow, the flow of electricity, now which for us we call it current. Okay. Hint: the phone, TV, and flat iron have resistances of 10 ohm, 20 ohm, and 50 ohm respectively. Alright, good. There we are. So the same task. You have been selected by a team from this company, so they started working seriously. Here we are. From UECDL. I think I'm not the only one who gets problems pronouncing this abbreviation here. They should really look into it. Anyway, to help the villagers address their concerns. Alright, good. Let's go and see the questions. Okay. So here we are. Let's move. So let's see. Except the main switch. Which switch, when put off, makes more than one appliance fail to work? And which appliances? Oh, so they're like, which switch in the diagram we had, which switch do you think which when put off makes more than one appliance fail to work and which appliances. Then also, hence, provide the best solution to address the problem. Yeah, you must come in and give us the best solution for that. Remember number 2, the saying. How much electricity flows through the TV? Yeah, we must calculate this. Then part B, help the villagers to establish why. Remember number 1, power becomes weaker along the way. Yeah, why does the power become weaker along the way? Should I talk about that? Remember number 2, electricity sent over long distances is at very high pressure, which is voltage, but very little flow. Why is it so anyway? Part C, using the diagram, explain to the villagers how a changing current generator at the dam in Jinja works. Yeah, this is very, very enticing, especially this part C. If you're a teacher or a student, you must wait until when you watch this part C here. Please be there to watch at least. In fact, where necessary, the whole item. Alright, good. Now, with that and without wasting time, let's get this answered. They're saying, except the main switch, which switch, when put off, makes more than one appliance fail to work, and which appliances? Okay, hence provide the best solution to address the problem. Let's go there. Okay, now it all begins with this. First of all, before you get this answered, what you must know is, this is now our alternating current, and I want us to, okay, start up reasoning. Now look, the AC, we are assuming, what if when the AC is coming in this order? Now, we are assuming all the switches are closed. All the switches are closed. Assume that all switches are closed. We're just assuming all switches are closed. Right there, and all switches are closed, like that. Now, please, this switch K1, this switch K4, this is K4, and this is the switch K5, like that. Okay, now look, if all the, okay, I'm assuming that all the switches are closed. Now, when the current comes from this side, this current will be able to flow here, flow via this, and flow via this, and will come out of this level like this, comes, part of it enters here. Meanwhile, this is closed also. Also, we have another current. Remember, it is AC, so it can move in every direction. This symbol means AC. Please, if you can really see that, this symbol means AC. If they draw just a circle, then they put a wavy line. That is an AC. Now, current comes in that format. Also enters in this. Can reach the TV very well. This is our fridge. This is our cooker. This is our TV, and current is passing through here. Okay, like that. Now, remember, I'm assuming all switches are closed. When all switches are closed, okay, good. Now, still, current which is coming in this order will flow like this, via this, okay, now via this, okay, even here it is closed. I think that now current will flow like that and up to that level where we have the flat iron. Now the question at hand is, which switch when put off will make most of the appliances to go off? Which switch? Now let's begin. I'll pick another ink. That, what if when we try, okay, pick this. What if when we open, we open switch K and we open it like that, switch K is open, who will go off? Remember, if switch K is open, it means that this current will come like this. When it comes here, it will not have any journey. Therefore, of course, this is open, there is space here. Okay, now realize that in that context, current will not be able to flow this side, so the fridge will not work. But current will be able to flow this side, and it will as well work. Remember, the other ones are closed. It will work here. It will pass through this, so the rest will work. So in switch K1 is open, only the fridge will not work. That is game down. What if when, okay, again, we say switch K1 is closed. We close it. Let's now go to this level. What if when we open switch K2 now? We want to see what will happen. When we open switch K2, current will still come. Now, as the current comes like this to flow this side, remember this part is open already. When this part is open, current will not reach the cooker. So when switch K2 is open, cooker will not work. So that's, you find that switch K1 affects fridge, switch K2 affects cooker. Please, the same effect, switch K3 affects only the TV. If you can really see that. Then switch K4 also affects only the bulb, according to the theory, because current can pass through this line here and it can be able to reach this side, even when, look, even if when we try with this, I'll use some here. Even if we try to open all these switches here, look, if we try to open all these switches here, open these switches here, look at this, something interesting here. If you open that, All right, now when you have opened that, what does it mean? I'll break this ink again. It means that the current coming from here can be able to move through this straight line here. So even when those switches are open, there is no harm, because when this K1 is open, it only affects this. When K2 is open and the K1 is closed, it only affects this, it only affects this, it only affects that. So you realize that the current is able to move up to this side. Now what happens in the long run? I will erase this off first of all for clear indication. Now remember, when all these other switches are open, current comes like this. Current comes like this. Okay? Now, as this current is flowing, what must you expect? Once we keep this switch K3 open, switch K5, this is switch K5 open, it means that the current will not be able to pass here. Which current? In fact, when the switch K3 is closed, current will come like that, flow. Finally, our flat iron will work, flow again, back here, and our radio will work, flow again, back here, and our bulb will work. Are you seeing? When switch K5 is closed, even when the rest are open. Now it means that, what if when we try this? On the contrary, what if we try this? When switch K5 is open, when the current comes over here, it is really so sad. You see that emoji? Current cannot pass through these levels. It means that current won't reach the flat iron won't work. Current won't reach the radio won't work. Current won't reach the bulb, so bulb won't work. So which switch, when switched off, can make most of the appliances not work? It is switch K5. Which appliances? Bulb, radio, and flat iron. Reason? It's because, now let's look at the arrangement. Are you able to see that all these other stuffs are in series? In series, what I'm meaning is, look, what you mean by series arrangement is this. Let me use this. Now series means that if current is coming, it can easily pass through this and continues in that order. When current is not diverted, it is moving in a straight line. That's what we call what? Series. If you can really see that. Series. Then what about parallel? Parallel is this. Parallel is this. Parallel, we have it in this format. Okay, trying to get here a sketch. A simple one to understand what parallel is. Parallel arrangement. So now the parallel arrangement here means that if you have a certain current I, just like we had right here, when I have a certain current I, here when it reaches this point here, the current will divide itself. Are you seeing that? So here it divides. So in a circuit where you see that the current splits into two, that is now parallel arrangement. Parallel. And if you are to check here, look, do you see that here, when current is coming like this, so you realize that I said that switch K3 is in what? Is in series. So in a series, once you remove the switch, it can affect very many appliances. So it means that it is not good to arrange when wiring, it's not good to put all the appliances in series, because when one switch can easily put off very many appliances. Like an example is in most of the wirings in the buildings, especially bulbs, someone can just mean to say that let one switch control all the other bulbs. It means that all those bulbs will be put in series. I don't know if that can make some sense. So now it means that we should always arrange. It is advisable, please, to arrange, or when wiring, you must make sure that the connections are in parallel, not in series. Now let's see which ones are in parallel here. Look, when current comes here, current reaches this level, part of it goes down, part of it continues with the journey. So this is a parallel. If you can see that, current proceeds again here, it divides, comes this side, and another one proceeds. So this one also is in parallel. Comes here again, one continues down, and this proceeds. This is again in parallel. If you can see that, then comes like that. Part of it is divided here. So even partly the bulb would be in parallel with switch K4. If you can really see that. Man, look, here it is a continuation. Okay, the whole current is coming, not divided. Here, if this is closed, the whole current comes not divided, flows via this, not divided, flows via this, not divided, flows via this, not divided. Meaning that this is okay. Meaning that this one, the flat iron, the radio, and the bulb are in series. Partly even the phone, but the phone is not all that really. If you can really look into that. Now, what you must know is that the best connection is always, if we happen to use the series arrangement. Okay. Alright, so it means that it is always good to connect in parallel than in series. Please, here, let me just use even emojis to make you understand this. In parallel, please, in parallel, we smile. But of course, in a series, not really. In fact, bad news. There we are. Oh, sorry, I meant to have it downwards. Okay, so, all right, now, okay, so in a series like that, and where necessary, even the tears must come out. Whenever you think about series, let it this emoji come into your mind. When you think about parallel, that's the best solution always. And now, parallel is good in a way that even in a connection, we can get. In fact, parallel is just good in when it comes to arrangement. Now, in here, I hope you have now seen we are talking about a radio, a flat iron, and a bulb. They are in a series. So when you switch off K5, the radio will be off, the flat iron will be off, radio will be off, and bulb will be off. When you switch off K1, when others are connected, now what I mean by switching off, when we switch off this, the others must be closed. We are sampling all closed, we switch off one. So when you switch off K1, only the fridge will go off. When you switch off K2, only in parallel, one switch goes with one appliance. So K1 goes with that, K2 goes with that, K3 goes with that, K4 partly with this, though in a series, in the long run, the bulb also can be affected by K3. Okay, so without wasting time, let's look into this in the description. So there. Alright, so now we have it that, okay, they're saying switch K5, yeah, we have specified, okay, appliances like a phone, flat iron, and radio. By the way, if you look at this in fact, you realize that, okay, yeah, if this is closed, since we switch off K5 when these other ones are closed, maybe just to give another explanation, since we just switch off K5 when these other ones are connected, it means that this one won't work, the phone won't work, because the bulb will work automatically, current will be flowing through it. The phone won't work, and even the radio won't work, because current comes like this, and ends here. Yet the one here can enter here, and we even had another one coming from this side like this. So the bulb will work, but a radio, flat iron, and phone won't work. So the appliances must be arranged. Okay, phone, flat iron, and radio. The appliances must all be arranged in a parallel. You see that? Clarified on that already. This ensures that each appliance receives the full mains voltage. Yeah, so in fact the in the parallel connection, all the appliances will receive the same OPD. The full main voltage is here 240. This now, what do we call this voltage here? This voltage is more like, look, now I want you to understand what this means in real life. Assuming you have a pipe carrying water like that. Now, in fact, what you must know is that, maybe say for example, we have a water pump, or this is a straw, and maybe this is your mouth covering up the straw. Oh, anyway, shouldn't be too fun. So that is your mouth covering up the straw. You see that? Okay. Now, if this is your mouth covering up the straw, and maybe this straw is placed into a certain liquid this side, I want to explain what this means. Now, the pressure from your mouth is the 240 voltage. Is it okay? Now, the water which flows in the straw into your mouth is what we call current. Now, what does it mean? That 240 voltage is the driving force which drives the current to move. So it means that without the 240 voltage, the voltage, we can't have the current. So that's what that really means. The pressure which your mouth exerts into the straw to pull the liquid into your mouth is what we call the 240. Because when you don't apply pressure, the liquid won't come. So when you apply the 240 voltage, the pressure in your mouth, the liquid will be able to flow, which is we are calling the current. Hope that really makes some bit of sense. So whenever you look at PD or voltage and current, that's what you can consider remembering that. So they're saying receives the full mains voltage 240 V, allows independent control of each appliance. Yes, if you find that K1 only controls this, K2 only controls this parallel. I've explained why it is parallel, that division of current. It splits when it meets at a junction and prevents one appliance from affecting the operation of the other. Yeah, in the series, one appliance affects the operation of the other. As simple as that. Hope that really makes a bit of sense. Let's still proceed. So now let's go to another part. So another part, they're saying that how much electricity flows through the TV. How much electricity flows through the TV. But again, what you must know is how much electricity flows through the TV. Here, somewhere in the hint, they give us this. Now, they have specified they only want something to do with the TV. Now, what must you know here is that, look, they gave us something like TV, the resistance of the TV is 10, if you can see that. Resistance of the flat iron is 20, if you can see that. In fact, let's see, I've not matched it well. Okay, so the resistance of the phone is 10, the resistance of the TV is 20, of course I've used the word respectively. Resistance of a flat iron is 50. But now our area of concentration is TV, which has resistance of 20. You see that? Very good. Now about a TV which has a resistance R of 20 ohms. Now what about the PDV? PDV from the main supply is 240. Yeah, in the picture, I think. Yes, in the picture here. Okay, if you can really see that, we have the PD supply is here, 240. Now what you're going to do next is we now go and make the calculation. It's just simple. So we're going to have this, like we say. Now, if you have, what do we want? They want current I. They want current I, which you don't know now. Which formula do you think has all these guys, these three? The VIR. So you said V is equal to IR. V is equal to IR. Substitute. V is 240 equals to the current I1 times the resistance, which is 20. Now you'll get that. Okay, a 240 is equal to a 20 I. Now what does it mean? It means that you divide by 20 on both sides, 20 on both sides. When you cancel that, you'll finally have the I as beautiful as what? Cancel this, cancel that there. So I will be the same as 12 ampere. Ampere is the unit used for measuring current. So let's go and look into that again. So we go there. I've clarified on that. You had V is 240, the R is 20, we don't know the I, so therefore from Ohm's law, we know that. Now if you don't know much about Ohm's law, you can go and watch item 6. Alright, good. So now V is equal to IR. I'll go about substituting in, and that's what you're going to have. So finally you'll have 20I equals to 240, dividing on both sides by 20, you'll end up having our I as 12 amperes. Yeah, so that's the current flowing through the TV. If they had asked for flat iron and so on, you do the same calculations, since they have given us the resistance and the V main supplies has also been provided. So we say, therefore, the current through the TV is 12 ampere. As simple as that. Part A Roman number 2 is done. Let's go to part B. Okay, now here we are. Now let's go to part B. Of course, we are done with this and we are done with that. Part B is saying, help the villagers to establish why power becomes weaker along the way. Yeah, by the way, why does the power become weaker? Why does it? Anyway, like when it has moved for long distances, why does it become weaker? Here we are meaning there's that situation when it's a bit rare anyway, but you realize that the bulbs can give just dim light, okay, whereby in the layman's language they will say there is little power anyway. So you're asking, why does it become weaker? Let's go into that straight away. Now, why does the power become weaker? Let's go there. So okay, now it all begins here. Let's get this right in the place. Now, in order for the power to become weaker, we are going to first of all go pictorial, because the pictures tend to make this bit simplified. Okay, but for those who watched item 6, that part when they ask for why does the electric wire become hot when they are using it. In fact, why does electric wire carrying current become hot in the long run? It's the same reason we give for why the power reduces when it is moving on a wire and in a longer distance. The same reasoning, that heating effect reasoning, is what we give here. Because the heat you see is the power dissipated or the power wasted, or anyway, that can really make some bit of sense. Now these two guys, you remember even in item 6 I used these very two diagrams to help us understand. Now it all begins with this. Like when you complete our circuit, you all know that current, remember that electrons flow from positive to negative like that. You see that? Now if electrons flow in that order, the current will flow in that order there, like that, going up, going like that. Again back here, and suddenly the bulb will give us the light. Now what must you know about this? What you must know here is that as the current is moving, just know this wire here, this wire you're seeing here, we zoom it maybe using a microscope, and that is these are the inside parts of that wire. Anyway, you just take an example, it is the inside part of that wire. Of course it's red, and you can see here the red color. Good. Now when you're in here, what you're seeing here as a negative, that is an electron. Because for current to be, in order for current to be in the place, there must be free movement of electrons. That's when you can have current in the long run. Now if that's our electron, imagine maybe this is our electron coming. As this electron comes, allow me to draw this. I think it is a bit the same, so you want to be able to see. So assuming this is our electron, remember these are the particles inside the wire. Yes, you all know that the wire is metallic, and the metallic has metallic substance is solid, and from the kinetic theory of matter we know that the solids have got small particles into them joined by stronger forces of attraction. So these are the particles inside the wire. They are not really looking like this, but we are just giving an example to help us understand this part. Now what happens here is that, why does the power reduce? In fact, the power reduces because of the heating effect of the wire. Where does the heat become? Where does the heat come from? Heat comes as a result of power loss. Whenever you feel heat in an electrical device, just know that the power is being lost. Just like when you're using your phone, the power drops, don't you see that? But in the long run, your phone becomes hot. So when you use your phone for a long time and the power is being used, you realize that your phone becomes hot. That heat means that there's power being lost. But how does that heat come about? When you explain it, then you will have explained why the power reduces when now realize that when this is the electron knocks with first of all, there are two theories. The friction between the particle of the wire and the electrons flowing through the wire, the friction alone, friction. Yes, I give an example that try to put your hands together and you rub them, your palms, you rub them for a long time. Do you feel that heat? Yes, I know you feel it. So that heat there, that's one way. And I told you, whenever you feel the heat, just know power is being lost. Now that's one way as a result of friction. You can see that. Another one is as a result of collision. How does that happen? So when the electron comes and knocks the particles of the wire, inside the particles of the wire, what happens is this particle, which has been moving at a very high speed, which you call kinetic energy, knocking this other particle, will make this particle to move the high kinetic energy, hence knocking another. But guess, at every point when there is collision between two bodies, there is always some spark-offs of some heat and light. You can really look into that. So that spark-off due to the knocking, kinetic energy gained from the kinetic energy lost from the electron and gained by the particles in the wire, will definitely do what? Bring some heat, and in the long run it will become hot. Now that heat there brings about what we call the heating effect, and the heating effect reduces the power. Hope that makes some sense. Now let's go and look into this. So the thing, when the current flows through the cable, electrons moving in the cable collide with the vibrating atoms in the cable, and lose lose some of their kinetic energy to the atoms. The atoms are these, so the electrons lose kinetic energy to the atoms. Okay, good. Atoms, these are the small particles which make up that wire. Okay, atoms gain more energy and vibrate with their large amplitudes, so they'll start moving up and down, up and down, up and down. So I mean by large amplitudes and frequencies as atoms rub against each other. Yes, I talked about that. That's not friction. Heat energy is generated. Now that heat energy is the power and is lost to the surrounding, making the power cables weaker. So heat energy, that heat you see, this heat here is the power in actual sense being lost, and that gets that explained successfully. All right, good. So without wasting time, let's go to part B, Roman number 2. Let's go there. All right, so you realize that let's see, look at part B, Roman number 2. Part B, Roman number 2 is saying electricity sent over long distances is at very high pressure, or in fact very high voltage, but very little flow. Yeah, high voltage, little flow. Now here, this rule objects Ohm's law, because Ohm's law says that the voltage V is the equal proportion of the current. That the more the voltage, the more the current. Now this rule objects this Ohm's law, because this rule is saying that voltage is inversely proportional to what? To current I. Anyway, it's a bit funny, but we'll get it explained. So by the in some cases, a certain law may be objected depending on some factors. Yeah, okay, because there's this one here, longer distances, and of course longer distances there is an effect of weather condition. Well, okay, there's the factor of weather. All right, good. The resistance of the conductor. Anyway, so let's, I think, go there. Now let's go and explain why is the voltage always high yet the current is very low for electricity sent over long distances. Still, I advise you go and watch item 6. You'll understand more about what happens when electricity is moving over long distances, and also in item 6 you'll get to know that why do we need transformers, and anyway, which types of transformers do we have, step down and step up. We all got them explained in that item 6. Quite enticing. Okay, so without wasting time, let's proceed. So now here we are. Right, so like it has been our culture, we first of all go pictorial, we look at it and we get it explained. We look at it and we get it explained. Please, we remind you that you must subscribe to the channel. Failure to subscribe, then be ready to pay in this time to come. So just subscribe and enjoy the free service. Just think about that. Just a simple subscription, you enjoy the free service. Okay, then also one advice I can bring about here is that please consider when the ads, maybe you're watching the video and an ad comes. I'm really sorry, I know this is a bit hectic to some of you, but always make sure you watch that ad at the end, because okay, YouTube as an app, it gives rewards for any video whereby the viewers are in position to watch the ads. So please consider watching the ads. It is the only way you can give, okay, you can appreciate actually the efforts put on this channel by just simply watching the ads. Just watch the ad at the end. It doesn't take more than a minute, so just be there. Even if you don't want it, just wait for it to go to an end, then we move, because YouTube tends to give us rewards basing on the number of times the subscribers are watching the ads. Anyway, we come back to work. Here we are. Now in this context, here they were asking that why is it that when power is moving for long distances, say for example we are in Uganda and we connect electric wires, okay, they are not always bent, but allow me, so electric wires up to what, up to Kenya, that's KY. Why does the power drop? Like say for example, if I'm just assuming maybe Uganda gives out 12,000 volts and Kenya only receives 10,000 volts. Please, these are just provisional values. It's not really like that. I just want us to understand. Now, where has the other power gone? Yeah, I mean, where has the 2,000 gone? Don't you see that there's something wrong? Okay, now this explanation will get you covered. So now in the long run, what happens here is you must appreciate two things. There's what you call power delivered and what you call power dissipated. Now, here, this dry cell has what you call the P is equal to IV. Okay, very good. Now, P is equal to IV is the power delivered. Power delivered. Do you really see that? So if that's our power delivered, now, what must you know? If that's our power delivered, this is IV by the way. I don't know whether P is equal to IV. Okay, so now that's the power delivered. Now what must you know is that in the wire, remember the wire has got a certain resistance R, and where there is resistance and there is also current I flowing, you see that? Where there is resistance and current I flowing, there will be somewhat some heat generated. I hope you can really see that. So if that heat is generated, it means that in the wire we have the power is equal to I. Okay, power is equal to I squared R. Do you really see that? And now this one here is the power. Okay, is the, in fact, is the power loss. This one here is the power. It is the power loss, in fact. So what must we expect here is that this one here is the power loss. Power loss. If you can really look into that. Now, if this is the power loss here, this one here is the power loss in the wire. This is the power we are delivering. Now, what must you know is that what does resistance affect? Resistance affects current. So you find that if you have 12 ampere coming, okay, you find that the bulb will only receive maybe, okay, 10 amperes. Then you're asking, where has the other amperes gone? Maybe they've been lost because of the resistance. Resistance means that if the current is coming in this order like this is the current I, okay, resistance itself blocks the current and wants it to stop. Now the energy the current uses to forego that resistance is the current we shall lose, and that explains why in the long run the current will reduce but the PD will not. Why? Because now the PD, I told you that in the dry cell you have the PD, the voltage, maybe the R is 1.5 V. This 1.5 is the driving force. I explained, if you can remember the other part where I talked about the straw when you are pulling the water. The pressure used to pull the water is this 1.5 V. Then the water which is flowing will be the current. So this 1.5 V will not change because of it is just a pushing force. But current will be lost. It means that it will push, in fact it will keep pushing. The 1.5 V will keep pushing the current. But remember the current has reduced, is now 10. So we shall have what we call a little flow in the long run, if you can look into that. So we have power delivered and power lost. Power lost due to resistance. Okay, so let's go there. They're saying, now that heat comes as a result of current being used. Whenever you feel heat, just know power is being lost. Whenever you see heat, just know that current is dying and reducing. So therefore in this context, current will be very low. We have I. So in this context, current will be very low and the PD will still be up. Okay, so okay, now I've explained that. So they're saying power delivered is P is equal to IV. That is in this right cell. I've explained. High voltage delivered results into small current flowing. Yeah, small current flowing. Yes. Then the power lost in a long distance cables is in form of heat given by P is equal to I squared R. Okay, now that this one come about, you all know that P is equal to IV. That's the formula for power. But you still all know that V is equal to IR. So when you substitute, P is equal to the I, now in a bracket, V is the same as IR. IR. Now the I times I will give you I squared, then the R will remain there. That's what it comes about. So, but you may not necessarily put this. You can just say power lost in long distance cables is in form of heat. Yeah, maybe you can win this way. You can say given by P is equal to I squared R. Okay, with no change in the resistance of the cables. Okay, because now you just appreciate that the cables have resistance. So therefore, once you see resistance, there's no current will be reduced. Okay, now as the current decreases, yeah, I told you of the 12 ampere coming from here and only 10 reaches the bulb. So when the current decreases, power lost becomes small. So it means that fine, we said that P is equal to I squared R, but even the current lost is too small. Just like from this, you see that out of 12, 10 has reached. So just only 2 amperes. Just think about that. Becomes so small. Okay, power delivered reaches its destination with little loss. So it means that the power delivered will reach its destination with little loss, because power delivered with it is the same as P is equal to I V. Now the V has not all that changed maybe, and the current lost has been just very small. So it means that there will be no big effect. Though still there will be the effect of the power loss will be very, very little. Okay, and that's what we mean by that. Hope that really makes some sense. Let's now go to part C. Okay, there we are. Now, good news. Part C, the longer awaited part, of course, shall have, in this context, we shall have the saying, part C. Using the diagram, explain to the villagers how a changing current generator at the dam in Jinja works. So, now I know. For you, when you think about Jinja, okay, some people, I know just your brain telling you that now turbines, are they turbines? Yeah, you're right about that. But maybe not really turbines. There is some more magic which you're going to look into this. Now, the story begins with this, first of all. Now, I want to see how an AC generator works. We want to see how an AC generator works. Okay, so we want to see how an AC generator works simply. Right? Okay. We want to see how an AC generator works. And please, the diagram of the AC generator resembles some other diagrams, but you don't need to be confused. In fact, here, we shall even make more clarifications. Maybe. Now, how is an AC generator made? This is how it is made. It is made of two strong magnets. You see, this one is the north, south. North, south. And of course, just like you're seeing there, just know that there's another north this side. And there's another south the other side. Okay, now. Okay, they're made of two strong magnets. That aside, now, this works on the principle that, okay, from Faraday's law, which we know that, okay, what they will do here, between the two magnets, they'll put a wire. This is our wire, like this. Our wire, like this. And this wire is connected to the brush B2. We have it there, that is a brush. And of course, I've told you that B1 and B2 are carbon brushes. Then, we have what we call the slip rings. Now, why slip is because, imagine, I must explain why they call them slip rings. Okay. Imagine you have that metal, then you have a metal, maybe a ball, or, okay, maybe, I don't know whether you know what to call a dynamo. A dynamo, that can be a good example, because now some people here, especially the students, maybe they didn't even grow up in the village, but I don't know if they know what to call a dynamo. Alright, anyway, the slip rings is just like, do you see what the cover on the water bottle, the mineral water bottle, that cover, when you're opening it, that kind of rotation, like it can just slide onto the cover, the bottle top, the cover can easily rotate. Now that's how the slip rings work. They are not necessarily attached to the carbon brushes, so the slip rings just okay, smoothly rub onto the brush, the carbon brushes. They are not permanently attached together. You get to know that. Now I have slip rings S1 and S2, then carbon brushes B1 and B2. Now this is how the diagram is, and if you're in an exam, please, this is what you need to draw. This one here, it's what you need to draw. Okay, as simple as that. Now this one I've only put it for some reasons maybe, which will come on later. And this one we call it the Fleming's left hand rule. Yeah, that is in the electromagnetism. Now what I want you to know is that, first of all, what we call the turbines. The turbine is the one which moves. Now what you're seeing here is what we have here right here. This is the magnet north, this is the another magnet south. Now this is the coil which you're seeing right here. Now the slip rings, we have this one and that. Then this metallic bar here, this wire which is inside the two, in between the two, okay, magnets, because we said that, okay, N and S are pole pieces of a strong permanent magnet. Alright, good. Now what happens here is that, now this piece here you're seeing here, metallic, it is always metallic like this. Now it is the one we have right just here. Now what is this X for? This X is showing that this part must be rotating, like this this wire here must be rotating, and we have it right here. Now it must rotate, but how can it rotate? It is rotated by what we call, okay, a turbine. The turbines, they are the ones which rotate this. I would call it maybe like a fan. It rotates, and when it rotates, even this one also will start rotating. Okay, it is in that position. It will rotate like that, rotate, rotate. So just know when this one is moving, what will happen? This one will start rotating, I think. Okay, now when it starts rotating, what must you know about this? Now, what moves this? One will ask you, now what makes this to move? What makes this to move? And anyway, why do we even need to move? What are the magnets for? Let's go there. Now, it all begins with this. All right, now this is how the AC generator looks like. For those who have ever gone the dam bridge, yeah, if you're taking physics, you can consider taking your students for a trip, maybe so that they can go look at this. Now, this is how an electric AC generator works. Now, because of the word generator, people think we mean this. Not really. Discard that. These other generators are not the ones they're talking about. However, though, they also produce electricity, but not really. The ones they use at the dam bridge are these ones here. Hope that really makes some sense. Now, this all begins with this. Now, what I was talking about is the roller. We call it the roller. This other part rotates. Now, the magnets and so on are inside this stuff, inside there. Of course, we can't see them. So, for us, we just split inside. We see the inside mechanism. Of course, the outlook can be designed in another different way. But now this one here is the roller, which goes to the turbines. But where are the turbines put? Let's go right there. So, where are the turbines put? Let's go there. Now, the turbines are put in this, in fact, where the turbines put. Okay, now, first of all, before we go there, we must appreciate this. We must appreciate this, that as before we begin, how does the principle of operation of the AC generator is the very principle we use for the electric motor. Now, electric motor, AC generator work on the same principle. And how it says that if a current carrying conductor is placed in a magnetic field, then the conductor will experience a force. Like what I mean here is, in simple terms, okay, in simple terms, what I'm meaning here is that, like, if we have, say, if you have our magnet here, and this is the north, and maybe this is the south, just know the magnetic field flux, magnetic field will be, okay, experienced in that area. Magnetic field everywhere. Think about that. Magnetic field everywhere. Now, what must you expect here is that here, what you're going to have in the long run is, if you bring a current carrying conductor, say for example, we have a wire, maybe this is our wire, carrying current, say I, and you pass it into the magnetic field, this wire will experience a force based on Fleming's right hand rule. Shall be looking into that. So this wire will experience a force, meaning that the wire can be pulled apart. Like say for example, the force I'm talking about is more like if you bring a north pole of a north pole of another piece of magnet, what will you expect here to be repulsion? That force you feel is what pushes this wire away. Okay, we shall go into that. Now, what principle is the electric generator based on? Yeah, the electric generator is based on what we call electromagnetic induction, but it all begins with this guy here, for a current carrying conductor placed between the poles of a magnet. Now that explains why we had the other diagram and we had a wire in the middle and the two magnetic poles on the sides. So let's now go and see what happens at the dam bridge. Here we go. Now at the dam bridge, look at this. There are very many ways on how they can make the other roller to move. I showed you the other thing which looks like a fan in the very first picture. Now at the dam bridge, you see this? This is what you have at the dam bridge. Like the rollers will be put here in a way that as this water moves, makes those rollers to move up. I don't know whether I can really figure out on this. Like they'll put, we call them turbines, and now they will make it easy. In fact, they'll just place it here in a way that maybe it's like that, in a way that when the water flushes this part, this part will start rotating. It will start rotating naturally because we want to produce the electricity on a low cost. We don't need to put in electricity again to move the turbines. So what happens here is that the running water, that's why they have partitioned it. You see how they have built the dam here, such that it can run at very high pressure. That high pressure can make the rollers to move. Now they press it in a way that the movement of water can easily move the rollers, and once the roller moves, it will be able to move the coil inside. Or if that is now in Uganda, in USA they use what we call a windmill to move those rollers there. They use a windmill like that, or if not that, then they use something like this. I might not go deep in that. Now what you want is the rotation of the roller, and this was introduced by a man called Faraday, and it's just right here if you can really look at him. Okay, now this Faraday said that for a wire, so if it is the magnet, I was explaining this, and this is a magnet. Now we have the magnetic field lines, we have them right here, right here, right here, right there. If you bring a wire, just naturally a wire like this in the magnetic field, then you happen to move the wire to and fro, to and fro, to and fro. Imagine I'm moving a stick to and fro, to and fro, or you keep swinging it around this area here. The theory says this stick will gain electricity, this heat will gain electricity. That's what we mean right here. It will gain some current. In fact, current will start flowing through the stick, and if you connect this stick here to a galvanometer, like this, once you connect it, the galvanometer will show some deflections, to and fro, meaning that current is indeed flowing. That is basing on Faraday, as I was talking about what we call the electromagnetic induction. Induction means that this wire is not even touching the magnet, this wire is not even touching anything, just in the air. That's what I mean by induction, without touching physically. That's what I mean by induction. Now the whole theory begins from there. Now how does the AC generator work? Please bear in mind that the wire placed inside between two strong magnets of opposite poles, once you move the wire to and fro, the wire moving, I'll use this. Okay, I think, assuming this is my wire and I'm moving it like that, at a certain point in time, there will be current flowing through the wire. How can you detect that? When you connect that wire to a galvanometer, you can indeed see the deflections. When you move the wire like that into the magnetic field lines or magnetic flux, then the wire will conduct electricity. So are you seeing even our wire, electricity started flowing? Do you see that? Those spark-offs? Okay, now let's still go on. So we have known that for a wire placed in between magnetic fields, it gains current. Now that current is what we could use in everyday life from the dam bridge in Jinja. That's the principle we use. Let's proceed to the next part. Now in the next part, you must know this, that as the current is flowing, it all follows the rotation. Okay, now this is our galvanometer. You see that? This is our galvanometer. Now before we proceed, what you should know is that as this wire, the coil inside the two magnets, rotates in that position, this vertical position here, there is no current which flows through it. There is no current. I want us to first of all note that before we proceed. In the vertical position where it is perpendicular to the magnetic field, remember the magnetic fields are like this, whereby the perpendicular magnetic fields are like this, whereby the perpendicular here, at that point, there is no current which flows through the coil. So there is no current there, and that explains why the galvanometer here is showing zero reading. It is at zero when there is no current. It can move this side when there is current. It can move this side like that. Now why do we call it AC? AC means that it is alternating. It can move in very many directions. At a point in time, it can come this side, come back here, or go there. To and fro, to and fro, to and fro. That's what I mean by AC. But how does that come about? It all begins with this. Okay, now what you must know is that how do we know the movement? We have not started. Remember, we had the two magnets of ours, the two magnets, north and south. Now we have our wire in between. Now this wire here has a roller on it, the other connected to the turbines. As the roller is moving, this wire here, we shall now want to know how will this wire move. Remember, these are strong magnets, by the way. Now what happens is, from Fleming's right hand rule, whereby this finger here shows motion, where will the wire move? Remember, the wire can move either this side up, as this one is going the other side down, if you can really see that. Okay, so now the second finger, this finger here shows magnetic field, and this other finger here shows current. Now when you bring it here, look, I think magnetic field is always from north to south. So your finger, this finger here, must point in that order, and you are right about that. Now, this must point in where the current is going. So once you point where the magnetic field is, these ones will show you the current and the motion. So current in this wire will flow in that order like that. Come over this side, back here, and back there. Hope you can really see that. Now what will be the motion? The thumb is pointing up, so this wire here will move up. Meanwhile, this side will be moving down. And that explanation is all in this picture. If you can really see here. Now you see the current is moving in this direction from Fleming's right hand rule. Please, you must now we show that Fleming's right hand rule. So it's going like that. Back here, current is coming out to this side like that. I hope that really that is making some sense. So take note that in all the descriptions about the AC generator, this side here, current must be going up into the screen, going in that order, and this side current must be going down. Now in the rotation, this wire when is also here, the current will also change direction. It will face this side, and so in fact, in this position, current up. In this position, current down. That's what I'm meaning by current into the screen, current down the screen. I don't know if they can memorize that. Allow me to resolve this. Please memorize this as far as AC generator is concerned. Whenever at this level here, current must be going up, and at this level here, current must be going down. So when it rotates, and maybe this one is A and this one is B, when A comes here, the same you do. When B comes here, the same you do like that. Okay, let's now move on. Now I'm first of describing without connecting it to the slip rings and so on. We are moving in steps. Let's go there. What about when we decide to proceed? Now in this first context, I want you to mark the colors. I want you to mark the colors here. Let's mark the colors. You see, this one here is pink, and this one here is okay, I will call it blue, B. This one pink, blue. Now pink is near north and blue is near south. Now we want to see, after rotation, we want to see that blue will be near north and the pink will be near south in another rotation. Let's go there and look into that. Okay, so here we are. This is a simple reminder, like this is what we had, and I had already explained this. Now when we come to this level, I think that now blue is rotating, blue is coming near north. Do you really see that? And the pink is coming near south, contrary to what we had right here. Okay, let's proceed. Now in the one would ask, what if when we just tie, what if when we just connect this to the bulb straight away? Connect this to the bulb. When you connect this to the bulb, these wires will entangle each other, will coil, and will even entangle each other, and now the bulb won't even give light because the wire can end up being cut, like you are seeing here. Look, if you connect direct to the bulb, it can't work because there's no, in this level we already have current flowing, ready for use. But how must we collect that current for better use? Okay, but bear in mind that now I want us to note something here. Please, do you see that I told you that in this position, when this one is rotating, you see that we had here pink near south, and blue near south and pink near north. In the other context, we have it that the pink is near south, we are rotating now, and the blue is near north. That's the difference you must put. This one, don't take it serious. I was only showing you that we can't just connect direct to the bulb. This connection can't work. What do we need? We need what we call the slip rings. So we need to put the brushes, the carbon brushes on this area, and another carbon brush on this area. The next we put the slip rings. That's the use of the slip rings. Now this slip rings here is, it only moves, like say for example, hold the water bottle in your hand. Hold your water bottle in your hand, then hold that there. Okay, the other open end, the top. Then start rotating the water bottle in your hand. Do you see what that happens? What happens there? That's how the slip rings operate. Now, your hand is like the carbon brushes, and the bottle is like the slip rings. That's how they work, not permanently stuck together. Okay, now, what are we going to have here? Now, in this context, I explained this, that the magnetic field lines are following in this from Fleming's right hand rule. The current will go up for that level, and current will come down in that level. I told you when it's in vertical position, no current at all. Now, what happens is, all right, now in this context, we have this slip ring B1 maybe, and slip ring B2. Let's use that kind of language. Okay, now, from Fleming's right-hand rule, I explained it already. You realize that when this one goes up, when this one goes up, this flows via this, current will come down via this. I explained how that current moves. Will come via this, flow into this, to pass through this carbon brush, like that, down this side, and back here. The bulb will give light, and back this side, and it goes back in that order. That is one direction, if you can really look into that in the first cycle. Now what happens here is that the carbon brushes, in fact, the movement has been from where in this level? It has been from, okay, it has been from, we have carbon brush B1. In fact, this one here is B1, and this one here is B2. So it is moving from B2 to B1. That's how current is moving. Why? It came like this, like this. It is coming from here. You see the arrow? From here, like this, to that side. So from B1 to B2. That's the kind of naming I've used. So still again, this one here is our B1, and this one here is our B2. There's something I want you to see. Our B2. Here it was from B1 to B2. Let's come here and see. Now, when it is rotating, remember I told you that when it is in the vertical position, no current at all. Now when it is rotating, remember, when it rotates in another cycle, remember here we had the pink this side, pink near, in fact, we had the blue near south and the pink near north. Now look at this next diagram as it is rotating. Just not it is rotating, moving, that kind of motion, just like you see, this moves up, this goes the other side, like this. Okay, now when it moves, remember now the pink is now coming towards the south and the blue is coming towards the north in this context. Do you see that? Okay, good. Now what happens is, I told you that whoever is in this level, current must be coming down, and whoever in this level, current must be going up. Do you see that? Memorize that, please, always. Memorize that. In fact, I will say, whoever is, this is maybe, allow me to call this left, and allow me to call this right. On the right, we must go down. On the left, we must go up. That's the kind of grammar I want us to use. So, now this one is already near north on the left, so the arrow must go up. This one is near south on the right, so the current, sorry, this is not the right way of having this arranged. Okay, according to, all right, so now this is our left and this is our right. On the right, current must go down. On the left, current must go up. You see that? The arrow must face up. Now the arrow comes in that format, like this. Now what you must know is that our carbon brush B2 is connected to this blue, and B1 is connected to the pink. Here we had B1 to B2. Here we want to see. So the pink comes, the current comes. Now the pink will give to, first of all, to this pink. Okay? So it means that, okay, to this pink, and now what are we going to have? It means that when the pink will give to the pink. Now the pink carbon brush is connected to this other part, B1. So the current will flow through B1, come over to the bulb gives light, come over this side, back here to carbon brush B2, meaning that at this level we are moving from B1 to B2. Are you seeing how funny this is? Look, in the first part we had B1 to B2, B2 to B1. In the next part having B1 to B2. Do you see that? Like in the first context, we had this B1, in fact we had B2 to B1. That's in the first part. Then we have B2, B1 to B2. Do you see that? It means that here current was going like this, and again it came back. Are you seeing B2 to B1, again B1 to B2? It moves in the opposite direction. Now that's why you call it SC, because it alternating, it keeps changing the direction. And how can that come about? It comes as a result of this. Now that graph, B1 to B2 will be this graph like this. Now at this level is when the coil is in the vertical position. When it is in the vertical position, I explained that. Now this one here is the B1 to B2. Now in fact B2 to B1, when now B1 to B2 will be this other area down like that. So it means that SC makes what we call cycles like that. Every time it rotates from this level to a vertical position, that's a complete cycle to the other side. So there is an SCY. We see that B2 to B1 and B1 to B2 like that right away. And now that process repeats itself. Remember, as it is doing so, the current is flowing, but it's an alternating current, whereby in the first phase, current is from B2 to B1. In the second phase, current is from B1 to B2. Now, this bulb here is the umeme, in fact, the UEDCL. This bulb here is the power we use in our homes. So from here, the power will be connected to the transformer, step-up transformer, which will increase the voltage, and it will be distributed into towns. Here I use the bulb, but just know this is where we pick the power from for commercial use. Hope that really makes some bit of sense. Let's move on. Okay, now that's what I'm trying to mean. The other steps coming on will just repeat what we have here. This and that will just have to be repeated. Okay, and suddenly the bulb will give light. Now just know, the more the turbine moves this wire to move at high speed, the more the current produced. The more the wire moves at high speed, the more the current produced. That explains why the turbines were put at near the Nile bridge. You would wonder where the power comes from. It doesn't come from water, but the water helps us only run the turbines, because we may not have the money to again have a generator, another generator, which uses maybe fuel like petrol to run the turbine. That would be very expensive. So we tend to use that running water to run the turbines. So it is not running water which produces electricity. It only runs the turbines which make this wire to rotate between two poles of a magnet, and that kind of rotation from Faraday's law, the current will be produced, and that's how we use. Just look at how cool that is. Cheap way to get electricity. Okay, now the journey doesn't end there. Let's come and look at this also. Okay. All right, so now realize that in that so doing, what I told you of B2 to B1, you see that movement, and from B1 to B2, it is a to and from movement. That's why we now call it an SC, because here the direction is like that, here direction is like that. It's changing direction, hence the word alternating. But what is changing? It is current. So hence the name alternating current, and that's why we call it alternating current, which can now be connected, and we use it in everyday life. So just like I explained it in item 6, alternating current is what we use in our houses. Okay, so this is what we call alternating current, and that's how it works. Even right now, the power you're using, that's how it is coming about. The turbines at the Nile bridge are very busy doing the work for you. Okay, as simple as that. So in this, let's go and look at the answers for this part. Okay, so maybe before that, now what we're trying to mean here is that I want us to maybe make more clarifications here. Let's make more clarifications here. Is that now here you know that the current is going up, current comes down like this. This current comes via carbon brush B1, you see that, downwards like that, via there, pass through this like that to B2. So B2 to B1, I explained that. Again it goes back normal way. Now again this one we have A right here, B right here, C right there, and D. What if when we move like this? I want you to understand something. Okay, what if when we move like this, and maybe here, okay, here we have our A, and this way we have our D, and this is how we have our B, and this is how we have our C. Look at it in that format. Remember I told you that whoever is here, current must be going up. Whoever is here, current must be going down. Now remember, as you have changed like that, just know that this AB is connected to which slip ring. AB is connected to a slip ring or carbon brush B1. In fact, just know that AB is connected to B1. Meanwhile, meanwhile CD is connected to B2. Now look, if this is AB as it's coming like this, it will go and visit B1, so it means that it will be from B1 to B2, like that. We look at who is in this position. When AB is in this position, it will be from B1 to B2. When, sorry, in fact, when CD is in that position, it will be from B2 to B1, hence alternating current. This is what the turbine moves. This roller here is moved by the turbine, which moves this wire. The more that wire moves from Faraday's law, the more power we get. Let's go there and get the description. So we are saying that, okay, so we get this explained. So we are saying that when the coil is rotated above the axis XY, now why is that axis XY for you? Axis XY is this one. Axis XY is this one, XY. And that is this roller here. That's what they're meaning, which is attached to this one and it rotates. So this one will move this side, and this one is going up. That kind of movement is what you're talking about here. Okay. Alright, so in fact, now you realize that, okay, when the coil is rotated above the axis XY, that's now done by the turbine, the magnetic flux linking the coil changes. Like the magnetic flux, those are the magnetic field lines in between the two poles. Okay, side AB moves upwards while CD moves downwards. I described that in using Fleming's right hand rule to know where this really goes. Like, let's go and look at this right here. In fact, what I was meaning is, from Fleming's right hand rule, this finger here shows direction of the field, and the field is from north to south. This is how the field line is moved. Okay, good. Now after doing that, when they are right angles, the fingers are at right angles, this other finger here shows us direction of current, and you see where it is going up. So that's how I have the current like that. This finger here shows that motion, where will the coil go. So this part will be going up and this other part will be going down. That kind of rotation is what we're talking about here. Let's go back there. Okay, good. Now let's get this explanation here. So they're saying an EMF therefore induced in the coil in the direction ABCD. I told that EMF, which is like voltage, is the one which drives current. More like if you are pulling or pushing a liquid in a straw, the force you use is the EMF. Then the water will be the current. So the EMF is therefore induced in the coil. Now once you see EMF, just know there is current which will flow in the direction ABCD. The direction ABCD, which I have just right here. Sorry. The direction ABCD. Okay. The direction ABCD meaning this. Though the used capital letters, but they meant to be small. Direction A, B, C, D. That's how the current flows, if you can really see that. Okay. Okay. Now, you realize that here we're going to have the direction ABCD, right? The induced current flows through the coil from brush B2 to B1. I explained that. Okay, next. When the plane of the coil is in vertical position, talked about this, the coil doesn't cut the magnetic flux, and so no current flows in the coil. So when the coil is in the vertical position, okay, the current doesn't flow through it. But anyway, how does it move? Remember, now the coil continues to rotate due to its inertia. Now, inertia means, like, say for example, if you're running at a very high speed, then you suddenly stop, you may end up falling down. Why do you fall down? Is because your body has been hooked onto, it is in motion already. So when you stop, your body will still be continuing. So that's what we mean. Like this coil has been rotating. So even if there is no current, the other force of rotation will still make it to move. And as it moves, it will now go away from the vertical position, and definitely it will gain again current. Hence the rotation will go on. Okay. Side AB starts to move downwards, and side CD starts to move upwards from the vertical position. Yeah, like what they are meaning. Okay, maybe I'll show you this here. Okay. So what the meaning is that the vertical position is this. Like originally, remember, we have side A, we have side B, we have side C, and have side D. That's the vertical position, no current. So remember it was moving. So the side AB will start coming downwards. That's the normal rotation. And the side DC will start going the other side, CD. I don't know if I can really look into that. So that's what the meaning right here. Okay. Okay, good. Now we proceed with this explanation. So side AB starts to move downwards and CD upwards from the vertical position. I've explained that. The coil cuts the magnetic field flux again. Current is induced in the coil, which increases to maximum. So the more it cuts the magnetic field, the more it rotates, the more the current produced. So just know that the current produced here is endless. The more the turbine rotates, the more the current is produced. Okay, when the coil is in horizontal position again. So when the coil is in horizontal position, there is maximum current produced. In fact, let's go and look at this. When the coil is in horizontal position, there is maximum current produced. Like say for example, if the coil is in this level here, had it here. Okay, when the coil is in this level here, like the way you're seeing here, then there is maximum current produced. Okay. All right. So let's get there back again. All right. So we proceed. Okay. So we are going to proceed. So we have the saying, the induced current changes direction and flows through the load from brushes B1 and B2. Yeah, I told you that side AB in this position here. Let me just make this clarification right here. I told you of this. What you should know is that this diagram is affected by who is in this direction, this position here of the wire. Like CD is there, but CD is connected to who? CD is connected to B1. So CD is connected to B2. Then AB is connected to B1. Do you really see that? Now, just say this one goes to B1 again, just interchanging, and this goes to B2. So that's how the current flow is. So when CD is in this position, we shall have from B2 to B1. Then that time when AB has rotated this level here, remember they rotate with their slip rings. It means that AB, the current will be from B1 to B2. Let's go and look into that. Okay, so from B1 to B2. All right. Now once you have finished this, look, we had B1 to B2 to B1. Then you had B1 to B2. Now the process is repeated. Of course, once you get that, this and that, the rest is just repetition. So the process is repeated, and the current through the load reverses the direction every half cycle. This stuffs I drew for you, like this, like this, like that. Like this side here is when CD is near south, and this side here is when AB is near south. That's what I mean by half cycles. Okay, when the plane of the coil passes the vertical position, hence an alternating current AC. So that's how the alternating current AC is produced. And this AC you're seeing here is the one you use at home. The bulbs you're seeing lighting, they use electric alternating current. Whatever you see apart from in fact, umeme or UEDCL uses what we call alternating current, and that's how electricity is produced, hydroelectric power is produced. Just think about how magical physics is, by the way. Very, 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 very interesting. Okay, we are ending there. See you again.